Hello and happy last Wednesday of April. This is actually my second attempt at making this video because it crashed during the middle of the first one. Maybe that'll make it better that I'm having to do it a second time. Wanted to follow up on some of the things we've been discussing for the last week, which is largely mixtures and some of the characteristics of those things. Following up a little bit further on mixtures are acids and bases, and these are terms that I'm sure you've heard before. And so what we want to do today is to go into a little bit more depth about what causes something to be an acid or a base. What are some of the characteristics of those things? We want to start with water because when we have an acid or a base, usually we have something that's going to be dissolved. And so up to this point, when we've been talking about water, we've talked about things that can dissolve into it and how that occurs and some factors that will make something dissolve better or worse or faster or slower. And if we think about water, normally we think of it as being our H2O molecule. This is kind of a representation of water. If we can remember that it's a covalent compound because its electrons are shared. And one of the things that we find when its electrons are shared is that they're not really spread out evenly with one another. So in the course of their sharing, what happens is the electrons tend to hang out on this side a little bit more often. And when that happens, that makes the hydrogen side a little bit positive and it makes the oxygen side a little bit negative. Now this is a word that I don't believe we are responsible for in physical science, but it is a term you'll see in biology next year when you come back to talking about water, is that water is polar. And it's kind of like the North Pole, South Pole. So there's kind of opposite ends to it. This has some consequences for how water interacts with things because, as we know, negatives are going to attract positives and positives are going to attract negatives. And that's one of the reasons why water tends to dissolve things very, very well, particularly things that have plus and minus charges, which we see when we have ionic compounds. So ionic compounds in particular dissolve very well in water because of this plus and minus part. Last week you watched a short video comparing and contrasting the dissolving of sugar and salt. And one of the main differences between the two was sugar is covalent, salt is ionic. And because salt being ionic, that means it's going to break apart and dissolve into its component ions. And so when we dissolve salt, we get sodium ions, we get chlorine ions, and of course the more salt we put in there, the more sodium ions we would get, and the more chlorine ions we get. Again, the reason why this happens is because the sodium is positive and it's going to attract the negative side of the water. The chlorine is the opposite. It has this negative charge, so it ends up attracting the positive side of the water. Since water is covalent, it normally is not going to break apart like we would normally think of that salt would into different ions. But if it did, one of the two ions that it could break apart into would be a hydrogen ion. Now, normally hydrogen has one proton and one electron. That's it. If it were to become an ion, it would end up losing this electron. And basically what all that a hydrogen ion is a little proton hanging out. So the reason we're discussing this right now is because if we put a substance in water and it produces a lot of these hydrogen ions, then what we end up getting as a result is an acid. The rest of the water molecule that's left is this OH with a minus charge to it. So you can see this is where we've got a missing hydrogen atom. But remember, the hydrogen lost its electron, and now at this point it's hanging out over here. So that's why we've got an extra negative charge to it. This OH is referred to as a hydroxide molecule, or an ion, actually better is the word. And if we get a lot of hydroxide ions in a solution, then this is what causes something to become a base. And acids are probably something we hear more often, and something you're probably more familiar with just in your house. But we have a lot of things that are also considered to be a base as well. And if it's a base, then it's got an excess of this hydroxide ion in it. One of the things we can do with a solution is to measure its pH. Again, this is probably something that's not unfamiliar to you, but you may not really have a clue of what it is. The pH scale gives us an indication of how strongly acidic something is or how strongly alkaline is, and this is another word for base. Okay. The pH, if you want to try to remember, the H kind of helps us to remember that we're talking about hydrogens, because if we have an excess of hydrogens, then that's what's going to cause something to be acidic. So I'm going to erase this. If we go back to our pure water, then this is kind of a neutral solution. We would not really expect there to be any excess hydrogens, nor would we expect there to be excess hydroxides. So we would expect nothing really in here to be there but pure water. If we move down the scale in this direction, and again, this is the same amount of water I'm going to try to draw every time, what we're going to find is we're going to start getting a little bit more H's all by themselves, because whatever we put in it ionizes and becomes an H. And so again, as we go down the scale this way, we're going to be adding more hydrogen ions. The same thing would happen in this direction, except instead of hydrogens, it's going to be the OHs. So it's still the same amount of OHs as that we would have over here of hydrogens. Just kind of an easy way for us to think about it. If you got up into higher level chemistry, this gets a little bit more of a complicated understanding of things, but we don't need to go there. But the idea is that as we move away from 7, we're getting higher concentrations, and there's the vocabulary word from this past week or so, higher concentrations of hydroxides, and as we get closer to 0, we're getting higher concentrations of hydrogen ions. Now, one of the things about the pH scale that is we always have to point out is that the pH scale is logarithmic. And I don't know if in your math classes you guys have done logarithms, but it deals with exponents. So as we go from 7 to 1, it's not a straight line. So in other words, as you go to the ends, it doesn't work, you know, that going from 8 to 9 is the same as going from 9 to 10 and the same as going from 10 to 11. What we tend to see is that these actually end up being a lot more like an exponential function. Is that as we get towards being an alkaline, at the ends, they get substantially more acidic or more basic. And what we really see is that there's a factor of 10 going on here. So if we have our water, or normal water, what we might find is that here at a pH of 6, there's only one hydrogen ion. And then if we move over to a pH of 5, we're going to get 10 times that amount. And then as we move to a pH of 4, we're going to get 10 times that amount, which would be 100. So every time we move over, we're going to be multiplying by a factor of 10. So a 2 is 10 times more acidic than a 3. A 3 is 10 times more acidic than a 4. You know, so therefore 2 is 10 times 10, or 100 times as acidic. There's some other scales in science that work this way. The scale that we measure with earthquakes is something similar to that. So a 7 on the earthquake scale is, you know, 10 times greater than a 6. A 7 is 100 times greater than a 5. It's 1,000 times greater than a 4, and so forth. The basic side works the exact same way, except the only difference is we're not talking about hydrogens like we talk about over here. We're talking about the hydroxides like we have on this side. And so again, we would have one part, this would be 10 times more, 10 times more, 10 times more, and so forth. So when we get to the very ends, we have really, really high concentrations of the hydrogen ions to make an acid, or we have a really high concentration of the hydroxide ions to be able to make a base. So looking at the pH scale in terms of some of the things that you may be familiar with, again, we'll start with the middle with water. Pure water should have a pH of 7. It should not have any extra hydrogen or hydroxides in it. And as we go down the scale, again, this is kind of weird, but as we go to 0, we're getting more acidic. And a lot of these are things that we drink. We can drink a lot of acids. So we have milk, coffee, tomatoes, vinegar. And again, remember, every time we go to a number, it's 10 times more acidic than the previous number. So the tomato would be 100 times more acidic than the milk. the lemon would be 10,000 times more acidic than the milk because it's 10 times 10 times 10 times 10. And by the time we get to our stomach, there's just tons of acid in our stomach. It's a very high concentration, which is good because it helps us to start digesting our food. If you've ever thrown up, one of the things you can tell, it really burns your throat. Your stomach is designed to hold that acid. It's got mucus on the inside of it, which keeps it from touching the stomach itself, so it protects it. People who get ulcers sometimes is because they lose that protective barrier. But if you throw up, maybe have felt that before, that sourness, that burning, then that's effectively just stomach acid coming up. If we go in the other direction, you see these are generally things we don't drink. We've got blood, which is slightly basic. A lot of the things in nature in terms of our bodies, the pH is very important. The pH doesn't need to be out of whack, for a better word. It's kind of like your body temperature doesn't need to be too high or too low. Our pH in our blood doesn't need to be too high or too low. Baking soda, stomach tablets, ammonia, soap, bleach, drain cleaner. Again, drain cleaner can be just as dangerous as the acid in a car battery because of how much they react with. If you think about it, what we're doing is as we get to the ends, we've got lots and lots of extra ions, and those guys are looking to react with something. They don't like to stay in ion. So the acids, those hydrogens, want to react with something, and on the other end, those hydroxides want to react with something. We can measure pH a couple different ways. One is the high-tech way, digitally, with a meter like this, and it's going to give us a really exact measurement. Environmental scientists may use this to check the pH of water in a pond or the ocean. People use it to check the pH of the soil, particularly if you're gardening or you've got a lawn that you're trying to take care of, because again, your plants are going to work best in a certain pH range. And if it gets too high or too low, we need to add certain chemicals to kind of get it back into its normal range. On this other side over here is litmus paper. This litmus paper that's over here on this side of this screen, these are just strips of paper that have been dyed with a certain chemical. Litmus is taken from lichens in nature. There's a lot of things in nature that will actually change colors in the presence of acids or bases. You can make some of these in your house if you have things like red cabbage or turmeric. But we have universal litmus paper, and you can see on here that it's going to measures all ranges, so you can use it for a pH of 1 to 14. And it's not going to be near as precise or accurate as a digital measurement, but it can just give us an idea of whether something's an acid or a base, and to some degree of how strong of an acid or a base it is. Even more limited are blue paper and red paper. The blue paper, we can use it to detect the presence of an acid, because if you touch an acid to it, it turns red. And then the red paper does the exact opposite, which is if you put it in the presence of a base, it's going to turn blue. So again, this is called litmus paper. And these are some of the characteristics we see with being able to use that litmus paper. There's a number of things that are acids that we come in contact with. This is just an image of 10 common ones. They sound all scientific, and to some degree they are. If we go through and look at these, acetic acid, boric, carbonic, hydrochloric, citric, some of these you may have heard of, but what I really want you to pay attention to is the chemical formulas in these, and hopefully you can see one similarity is that they all have hydrogen in them. Again, because that's what makes an acid. When we put these things in water, they're going to dissociate or dissolve into ions. And one of the ions that's going to be produced is the hydrogen ion. These are used in a lot of different processes. A lot of these things in our food. Acetic acid is what we find in vinegar. We find carbonic acid in sodas. We find citric acid in citrus products. And we find a lot of these things in cleaners as well. One of the characteristics that we also have with acids is that they react very highly with metals on the periodic table. And when this happens, if we have something like hydrochloric acid, what we get is a single displacement reaction, if you want to think back to one of our last units, because when we have one of these metals like the zinc or the tin, what's going to happen is that the metal is going to basically swap places with the hydrogen. And so if our metal was sodium, got our cute little cartoon over here, right? What's going to happen is if we took hydrochloric acid and sodium was our metal, then what happens is that sodium replaces hydrogen to produce sodium chloride, which is a salt. and then what we're left with is the hydrogen gas that's going to be coming off of it. So again, since acids have hydrogen in them, one of the common things we often see is that when an acid reacts with a metal, we're going to get a couple of things. One of them is often going to be hydrogen gas, and the other one is going to be a salt. It's not always sodium chloride, but remember, a salt could be any metal. So here with the chlorine, all of those would be salts. So copper chloride would also be considered a salt. It's not the kind of salt we would eat, but in chemistry, it would be. There's a number of things that are bases as well, and just like with the other image, what I want you to notice not necessarily what all these things are, but chemically speaking, what is their similarity? Because with the acids, we had hydrogen. With the bases, again, we come back to this OH, this hydroxide. So when we put these in water, they're going to break apart into their ions. And so again, you'll notice these are all metals. So sodium, potassium, calcium, magnesium. So we have metals, which is our positive ion. We have the hydroxide, which acts as a negative ion, and that's what's going to cause something to be a base. Again, and the stronger the base is, the more concentrated it's going to be, and the more completely it's going to dissolve into those two ions. A lot of our bases are used as cleaners, oven cleaners, drain cleaners, Drano, lots of things that are kind of nasty and you don't want to be involved with. So sometimes we think of acids as being very dangerous to be around, but very strong bases can be equally as dangerous to us. Okay, so in getting close to wrapping up, we can characterize acid properties and base properties. Notice they both conduct electricity. The reason why is because when we put them into water, they separate into positive and negative ions. As we saw earlier, we can detect their presence with litmus paper. One of the things about acids is they tend to have a sour taste. So this is the point where I say don't go around tasting things to find out if it's an acid. But a lot of things that we do eat have a sour taste to them because of the presence of an acid. We tend to put vinegar in things, or sometimes even with sodas, we want something to have a sour taste to them. We don't have any tasting properties over here with bases because we really don't need to be tasting those. One of the things that they do, though, however, bases tend to have kind of the slippery, soapy feeling to them. We'll talk here to wrap up with about this idea of neutralizing. And then the other thing I said that acids will often do is that acids will react with metals, and in the process, they will release hydrogen gas when that occurs. So lastly, what happens when we mix an acid and a base? So if we go back to thinking about what these things are, bases have hydroxides, acids have hydrogen. If we mix these things together, you'll see that we get water. And we call this a neutralization reaction. And so if we go back up here with these properties, we see a number 4 on both of these sides. It says these react with bases to neutralize their properties, and bases react with acids to neutralize their properties. So we can have a really nasty base, like a drain cleaner, and you can have a really nasty acid, like car battery. And when we put them together, it's kind of like they cancel each other out because they reassemble. They come back together to form a water molecule. There's also usually a salt that's going to be formed with it as well, because these would probably not be the only ions that would be involved. There may be some sodium that was with this. There may be some chlorine that was with this. We might get some salt as well. But we have what's called a neutralization reaction. And that's why back in one of the first slides that we had earlier, I go back up here, stomach tablets and stomach are kind of on opposite sides. So one of the things the reason we use stomach tablets is because they have they're a base, and what they do is they neutralize some of the acid. So sometimes our stomach gets too much acid in it, and we want to fix that problem, and so we can put that in there. So hopefully with this, it kind of goes through and gives you a summary of what are acids and bases, chemically, what causes an acid to be an acid, what causes a base to be a base. Hopefully you understand a little bit about the pH scale and how it works, and some of the characteristics of acids and bases as well.